times about differential equations and integration is you can't actually work yourself backwards to get a particular solution. So we need to have other techniques to get an idea of what our particular solution is, and one of those is something called a slope field. Now initially, I'm going to tell you slope fields look scary because like, what the heck is this? But they're actually not bad at all. All that a slope field is you take your differential equation, and you know that your differential equation is an equation of slope. So all a slope field is drawing little tiny slopes at every single possible point that exists. Okay? So, for example, you could take the point 1, 0. Would you agree at that place your x value is 1, your y value is 0? If I plugged my x value of 1 into my derivative, I would get a slope of 2. So I go here, and to my best of my ability, I draw a tiny little line that has a slope of 2, to the best of my ability. Now the interesting thing about this equation is this differential equation doesn't have a y. So you'll notice that all of these slopes, when x is 1, they're all the same. Because the x value would be 1 at all of those points, the y value changes, but that doesn't affect my formula for my differential equations. Some differential equations we have will have x's and y's. This one just has x. Okay? For example, when x is -1, can you see that you would have a slope of -2? So every single place where x is -1, I would draw a slope of -2. This is all a slope field is just plugging in a bunch of points, figuring out what the slope would be, and drawing a tiny slope like that. So for example, right, I could take any point on here. I'm going to take the point 2, 3. My x value is 2, my y value is 3. In this slope equation, in this differential equation, the y does not matter, because there is no y on the right-hand side of my equation. But if I plug in 2 for x, my dy dx would be 4. So at 2, 3, which is this point right here, I would, right, at x equals 2, dy dx is going to equal 4. At that point, I would, to the best of my ability, draw a slope of 4. Now this example that we have is a differential equation you definitely could work backwards. Okay? Can you see that it would be so easy to say what y is equal to? It's going to just be x squared plus c. It's just your regular x squared graph. Now, for the purpose of this, let's just pretend c is 0. You guys know what an x squared graph looks like. But if c is 0, we definitely would have the point 0, 0. So what we're going to do next is we're going to see how does our slope field allow us to draw our parabola even if we didn't know it was supposed to be a parabola. And this is the purpose of slope fields, because sometimes you won't be able to get the x squared plus c. But you're still going to be able to graph the original function using your slope field. So, what do we have on our slope field at 0? We had a flat line, so I'm going to draw a flat line there. And then I'm going to say, well, if I kept going flat, my next slope bends me up. So I have to bend up at that next area in between those next two slopes. And then it bends up again and again and again and again. And you just sort of follow your slopes and keep drawing according to that slope, and as soon as you get to a new slope, you bend a little bit more. And does that not look like a parabola going through our slope field? So here's a slope field that has an x and a y and a 1. Okay? Here is the slope field for this. So we're going to just look at a couple of these and see why it happens. First of all, can you see when x and y are the same, they would cancel out in my differential equation. If x and y were both 3's, you'd have 3 minus 3. If they're both 2's, you'd have 2 minus 2. And if x and y are the same, then y prime would always be 1. Notice these slopes here all have a slope of 1. At every point where x and y are the same, those slopes are all equal to 1. What's annoying about a slope field? How many you have to plug in so many points to get all those little tiny little lines, right? How do I know that this line right here, this is a good point. How do I know that at 0, 1 it's going to be flat? Well, if I plug in 0 for x and 1 for y, I get 0 minus 1 plus 1, I get 0. What does the slope of 0 look like? A flat line. And apparently, if you plug in 1, 2, can you see that if you plug in 1, 2 into your differential equation, x is 1, y is 2, you get 0 again. So we have all of these places where we get 0. And after your slope field is created, you can find a particular solution. So what is the particular solution that passes through 0, 1? Well, we know we have this point. And at that point, my derivative was flat. So I start at that flat line, and then I'm like, ooh, now I'm hitting a slope that is a little bit curved, so I've got to go towards that slope. And then it's more. Here, in between these two, I pick a slope in between those two, and you just follow your slopes as you go, and you create your curve. And so even though we don't know necessarily, well, this one we could do our separation of dy and dx and actually integrate and figure out our particular solution, okay? But now we have a graph, and we could use that graph to estimate all sorts of things. So, what do we do for these next couple questions? You've got your equation. Figure out your dy dx. Do a bunch of mental math. Fill in that chart. Then, to the best of your ability, draw those slopes at those points. All right, do you want to check how you did on the second one? Does your slope field look something like that? So we have some undefined ones. Those will go straight up and down. You know what's really cool about this slope field? Let's say I take a point in between. And I'm like, okay, I want to draw my actual function that would have gone through here. Look at this one. It would be flat. Then it would turn. Then it would go flat. Oh my goodness. A perfect circle. So you have now a differential for a circle. Sorry, I just think that's cool. And if you take the equation of a circle, x squared plus y squared equals 4 equals 6 equals 9, and you did the derivative with implicit differentiation and solve for dy dx, you would get this as your differential equation. And here's the last one. Plug your values in. So just curious, is this 10 out of 22, 3 out of 22? Is it like, got everything right, but then off there, or which one? I thought it was much better. Okay, try your hand at matching. See if you can come up with some good clues. See if you can see some patterns. Like, what pattern do you notice in 5, 2, 1, 2, 5, and 7, and 4, when one variable is missing? What patterns do you notice? Right? Because some of them have only x's, some of them have only y's. What pattern do you notice? Oh. And then we'll match. Okay, I want to next do 2 and 7 because I want to do the ones that only have x's to look for a pattern. So I'm going to look at 2 here. I don't know if you got 2 is equal to c. Okay. Again, if you work yourself backwards on that one, can you see that you would have an x squared graph? So we can sort of think which one of these would give me a parabola if I go through those slopes, right? So again, here, I'll do it more carefully. That would be basically the shape that I get going through those slopes. That gives me a parabola, right? And then I also wanted to do 7, right? That's also going to be a parabola. That's going to be h, and I hope you can see that through this one. You would also pick any point, you would draw a parabola through those slopes. But what I wanted you to see in 1, 2, and 7 is there's a pattern if there's only x's and no y's. What is the pattern in 1, 2, and 7? Don't blurt it out, but look. Look at E, C, and H, and see what they have in common when there's no y. How many people think they see a pattern? Couple? We'll keep looking for a bit. Let's see if you can see a pattern that happens when there's no y. Are we all good, or do we want the pattern explained? You want the pattern? Could someone tell me a pattern they see? They all have a dip, but I have dips in some of the other ones too. So I'm also looking for a pattern that is in those graphs that's not necessarily in the other graphs.
Like if you were to shift the feedback over so you could see more of it, like would they all be symmetrical like the y-axis? Like you could flip them over the y-axis.
Right. You could get this one shifted over. That's going to be symmetrical about the y-axis. Is a coincidence in those three because they're all even functions. So that's true, because an even function is a reflection over the x-axis, and it happens to be that x squared is always going to be an even function if it's shifted over, and cos of x is also going to be even because it's shifted over. These are good. These are good patterns so far. And this is the problem with me giving you a pattern on only 3, because you will see some other patterns as well. What else do you see, Kate?
The slope lines are like on a vertical like thing.
Yeah, on like, if we look at vertical, like a column, you see that all of those are the same there. Okay? On this one, pick any column, all those ones are the same on H, and on number 2, which is C, I pick any, here's a nice flat one there. And that should make sense, because as you go up and down, what's changing is just your y value, and your x value stays the same. But in 1 and 2 and 7, there is no y value to change the slope. So if you have a slope field with just an x, as soon as you find one, you have that whole column is going to be the same all the time. And we're also going to find out with the ones that just have y's. So number 5 just has a y, is G. Do you notice that the row, all the rows have the same slopes because the x value doesn't affect it. And which one also, looks like number 4 only has a y, it's B. Do you notice that these ones stayed the same in the rows? That means the x values do not affect the slope, only the y values affect the slope. What happens if all the slopes are all the same all the time? Then you would have no x's and no y's. It would just be the slope. And the last couple, 3 is F, and 8 is D. For matching, one of the things you could do in a matching one is start off with the easiest math to do and plug in 0, 0. So if I plug in 0, 0, I'll write this. If I was matching, I'll do this in purple. If I plugged in 0, 0 here, sine of 0 is 0, I would need a flat line at 0. That definitely does not look like what's happening in A. Could be here, could be flat there. Doesn't look like you'd have a flat line in between there. In fact, in between there, not really, but sure enough, here it looks like we could have a flat line at 0, 0. Looks like that's what our slopes seem to be coming together. It would be even nicer if this slope field had plotted those points exactly on. They kind of plotted points in between, which made things a little bit more difficult. Okay? At this one, at 0, I would have a -1 slope. So does that look like that would fit in my slope field? In that. X minus 0, 0, this one would have flat again. So in F, does it look like flat would fit? And this one's got a kind of a neat pattern where if you go on diagonals, things seem to match up. So that could be a strategy that you could use. 0, 0 would be flat here again. Unfortunately, this is not the greatest strategy because this one's undefined. So that would be up and down. And this one would be 2. So using 0, 0 could help us find out number 5 would be G, because this one definitely looks like the slope field at 0, 0 would not be flat. But it didn't really help us differentiate between a bunch of other ones. So then you'd have to pick another point. Something else that you could easily figure out. So some generalizations we've noticed. If the slope is 0, that's a little horizontal line. If it's undefined, it's a vertical line. If your slope is positive, your derivative is positive. If your slope is negative, your derivative is negative. All of these things should make sense because your derivative is basically a slope formula. And these are the patterns we just noticed. If you have parallel dashes on the vertical axis, that's when we saw that the columns were the same. There's no y value. And when we noticed that the slopes along the rows were the same, there was no x values. And when we talk about periodic dashes, okay, right, it's going from left to right, or even, yeah, we're going from left to right, it's going back and forth between the dashes. It has a period. It means that your derivative is periodic as well. So that helps us with number 1. So you have the slope field there. It's given to you. If they give you the initial condition 0, -2, draw that point on your slope field. And then follow your slopes to draw the rest of your graph. So basically you want to just keep going along the same slope that they give you, and as the slopes change, your graph will change. And we get a beautiful parabola shape. Of course, for this kind of equation, you wouldn't need a slope field because you definitely could figure all of this out with your regular integration. Right? Our regular integration would say our initial function is x squared plus c. If we know that y is -2 when x is 0, we could solve that c is -2. So this equation should be x squared minus 2. But now, let's take that equation, since we know it, and see how accurate our slope field was for giving us our graph. Okay? X squared minus 2, you know how to graph that really well. You would know that it should go through 0, -2. Now that point should be perfect because we were given that point. But if I go over 1 and up 1, I should have 1, -1. And then if I go over 1 and up 3, I should have the point 2, 2. Pretty close. Just by following the slope, see how close yours was. Did you go through those points? And you were just following the slopes, and your slopes were telling you where to go. So it's kind of a neat check. How close were you to the actual graph? And it's pretty hard to go off by too much unless you don't follow a slope right. So here we have a differential equation, xy over 2, and its slope field is given. If we want to calculate the slope at 1, 1, which is highlighted right there on our slope field, we could plug in 1 and 1, and we get 1/2. Does that seem to look like a slope of 1/2? Seems decent. So now f is the function that satisfies this differential equation, and we want to write an equation of a tangent line to this through the point 1, 1. Well, we've been doing equations of tangent lines for a long time. In order to write an equation of a tangent line, we need a point, which we have, and we need a slope. Well, the slope, we can either look here at, we could estimate it from our slope field, but since we have the equation, we've already figured out that our slope is 1/2. So, slope is 1/2, point is 1, 1, point slope form. You're going to start to find that using the point slope form is a very quick way to write equations of lines. Beginning of the year, you were probably tempted to use y equals mx plus b more often, and maybe by now you're starting to be like y minus y1 equals mx minus x1. It's so easy to use because we always have a point in the slope. You just plug things in right away. Now we're going to use our tangent line to estimate the value of f of 1.2. Do you remember what this was called? I can't remember what unit we did it in, but this is called you remember linear approximation? Linear approximation says that when you zoom into a graph, the tangent line is pretty good at estimating things nearby. So at 1.2, that's really close to 1. If I use my tangent line that I created here and plug that in for 1.2, this will be a pretty good estimate. Not perfect, but a pretty good estimate. Why is this helpful? Because we don't actually know what the real equation is. Could we maybe split this up and integrate? Yes. We could probably split this up and integrate and solve for c and find the actual equation. However, it might be more work than this approximation. And if we just need to know what it is close to, okay, now we're getting it, I know, I'm getting more into science and engineering and applications of math. In the real world, we're often okay with close enough. I just need an idea so I can keep going in my thoughts. Linear approximation is beautiful for that because it's really simple. How would I find out what it actually is at 1.2? Well, first of all, I would have to do dy equal dy, I'm going to split this up, right? dy times, move the y to this side, equals x over 2 dx. I could integrate both sides. I would have the natural log of y plus c on this side, and if I integrated this side, I would have x squared over 4 plus c on this side. So then natural log of y is equal to x squared over 4 plus c. Again, the c's just sort of combine. If I wanted to solve for y, it would be e to the x squared over 4 plus c. Base is e. There's my equation. I still have to solve for c. So I know it goes through the point 1, comma 1. So when y is 1, I hope. Okay. What's c? There we go. C would have to equal negative 1/4. So now I have the following. There's my actual equation for y. Mental math. Plug in 1.2 for me. Tell me what it is approximately. How good is your mental math at 1.2 here? Okay, quickly do 1.2 squared. Right, that's not too bad. That's 1.44. 1.44 divided by 4. Subtract 1/4 from that. And then do e to that power. Mental math is gone. It's like, I definitely need a calculator. I need a program to figure this out. I'm terribly curious right now. I shouldn't have done this. But how close is it to 1.1? Because 1.1 is our estimate using linear approximation. It better be somewhat close, otherwise my whole spiel here is going to be wasted, or maybe did I make a mental math error anywhere that anyone can notice? I sure hope not. Of course, my graphing calculator is super fast at this moment. You know there's an E button? Did you know there's also an e to the power button? Right here, which is, of course I can't see it right here, but second log. No, that's 10 log. Here. Second ln. You get the e and it automatically does the power, saves you one button. And now I can do, what did I want to try? 1.2 squared divided by 4, subtract 0.25 or 1/4. 1.11. And our linear approximation came up with 1.1. We're off by 16 1/1000ths. That's not bad. And as far as mental math goes, this I could have done easily without a calculator. This required me to do a lot of higher level math to get the actual value. So this linear approximation that we had before, it says that for values really close to your point, your tangent line is a good approximation. So again, we had a slope field. And what's nice about our slope field is if you wanted to, you could now graph y equals e to the x squared over 4 minus 1/4 relatively accurately using your slope field. I'm going to go, I'm going to say, well, it went through this point. So I'm going to go through my slopes. There's our graph of e to the x squared over 4 minus 1/4. Approximately. Kind of looks like a parabola. But it's not. Very cool. Draw the solution to the curve going through -2, 0, and 0, 1. It goes through 2 points. Well, no. Use different colors. So draw 2 of them. Draw one of them with one color going through -2, 0, and one of them with a different color going through 0, 1. they look extremely different. Just out of curiosity, could you separate the variables on this one? Well, first I'd want to multiply both sides by dx, but then I have a problem that I can't just move this y squared over to the other side. I can't just divide. I actually can't separate my x and y nicely so that my y's are with my dy and my x's are with my dx. We have currently no tools for this equation to find the particular solution. The only tool we had right now with x's and y's was to separate the x's and y's and have them on separate sides. But this one, when I try to do that, I get a problem that my y is still stuck with the dx. I can't just divide by y squared, because then there would still be a y squared divided on this one. I can't separate them. I'm stuck. The only thing I could do was create a slope field. And then if I had a specific initial situation, for example, in the blue one, I have -2, 0. I know that that's the case. Then I could follow my slope field and say, this is what would happen for the rest of the points on this graph. And I hope you also notice that that shape that we came up with is like, I have no idea what that equation is. It doesn't look like anything I've ever seen before. So this is an example of where a slope field is the best thing that we have to find out what's happening in real life and to create a model. All right, bell is about to go. So we will leave these last couple.